Chapter 3, Systems of Linear Equations and Linear Inequalities. Section 3.1, Solving Linear Systems by Graphing. So when you graph two lines, one of the following can happen. I'd like you to pause this right now, and if you're writing in pencil, jot down in 1, 2, and 3 what three things you think could happen. So if you're graphing two lines, one thing that can happen is that they intersect at one point. This is probably what's going to happen most frequently. And what you need to remember is that if they cross once, there's one solution. And that one solution will be an XY ordered pair. The other thing that could happen is that they could be parallel. Parallel lines, remember, never intersect. So again, if they never intersect, there can't be a solution. And the third thing that can happen is, though they might not appear to be the same line when you first see them, once you solve them for y and get them in the form of y equals mx plus b, you'll realize that they are the same line. So again, if they intersect everywhere, then there's going to be infinitely many solutions. So let's take a look at a couple of examples. So first of all, we're going to graph y equals 3x minus 1. This is already in slope-intercept form. So we're just going to go to the y-intercept of -1, and then my slope is 3, which means I go up 3 and over 1. Up 3 and over 1. Now, since we're finding systems of solutions to systems of equations, we need to make sure that we're graphing our lines very carefully and plotting points through the graph, which is why I stressed doing that earlier or last chapter. Because if you just graph two lines and kind of slap your line in there, then we might not be able to find that point of intersection very easily. And so now this second line, before we can graph it, we need to solve it and get it in the form of y equals mx plus b. So subtracting the x from both sides, we get y equals -x plus 7. So my y-intercept is -7. It appears as though it's going to be up here off the graph, but then I'm going down 1 over 1. And as I plot these very carefully, we can see that they intersect. I plotted the same point at that point. And so when we look at what that point of intersection is, it is 2, 5. And remember that we can check our solution. If we plug this xy up into that equation and we plug it into that equation, it should be true. So let's go ahead and try that. If we plug it into the first equation, we're going to get 5 equals 3 times 2 minus 1. 3 times 2 is 6, minus 1 is 5, so it works. We plug it into the second equation, x plus y, well 2 plus 5 is 7, so it works in the second equation as well. Let's go ahead and try this second example. So again, we're going to have to solve the first equation for y, so why don't you go ahead and pause the video and do that on your own. So for this first line, since there's no coefficient in front of the y, we simply have to subtract the 3/4 x. So now I can graph that line, a y-intercept of 5, and I'm going to go down 3 and to the right 4. And then down 3 again, and to the right 4, which would put us way out there. So when I graph that line, and now go ahead and pause the video again and solve the second equation for y. And so when we graph the second line, we see that it has the same slope, therefore the lines are going to be parallel because they're not going to be the same line because they have a different y-intercept. But I want you to go ahead and plot this line anyway. So a y-intercept of 2, down 3, to the right 4, or we could also go up 3 and to the left 4. And so when we graph this line, we can also see that they are parallel lines. So what is the solution? You still need to tell me that the solution is that there is no solution. So please don't be content with just graphing two lines and saying they're parallel. You need to understand that parallel lines means no solution. And now let's go ahead and graph this last pair of lines. So again, we're going to solve the first equation. Actually, the first equation is already solved for y. So if we were to graph that, we're way up here at 8, which is off my paper. But then if I were to go down 2, I'd be at 6 and back 1. So keep in mind if I go down 2 and to the left 1, that's the same as a positive 2 slope, and so that way I got it on my graph. So if I go down 2 and back 1, I'm still graphing an uphill positive slope. And now let's go ahead and solve the second equation for y. And you could pause the video and go ahead and do that. And so when you solve the second equation, you see that it is, in fact, the same as the first equation. And since I've already got that first equation graphed, I don't necessarily need to graph the second equation. But when I get to this point, I do want you to graph the line. We can all use some practice in graphing lines. But I need you to tell me also that this is infinitely many solutions. And this idea of finding those points of intersection is basically what we're doing in this chapter. So you need to remember that there's a relationship between finding that point of intersection graphically and also, as we move on in the chapter, finding that point of intersection algebraically. But when you find that ordered pair, that means where those lines cross. So that's a point that's on both lines. Now we're going on to section 3.3, and this is graphing systems of linear inequalities. And so again, we've graphed inequalities. I gave it away a little bit too soon. But anyway, when you graph linear systems of inequalities, not really 5 steps to do, but 5 things to keep in mind. First, you need to make sure that you graph and shade each inequality. And you need to be shading neatly because where all the shaded regions overlap is the solution. And so then you need to make sure that you're shading darker in that region so it's clear to anybody that's looking at the system and looking at your graphs what exactly is that solution set. Remember that if it's a strictly less than or strictly greater than, it's going to be graphed with dashed lines. If it's less than or equal to or greater than or equal to, you're going to graph it with solid lines. And also, it's not written down here, but keep in mind that when you multiply or divide by a negative number, you need to flip the inequality. And then the last thing to keep in mind is if there is no overlap, there's going to be no solution. However, this will only happen with parallel lines, but it's not going to necessarily happen every time you have parallel lines. So you still need to graph and shade your inequalities to see if they overlap. And so now let's go ahead and do a couple of these examples. First of all, in order to graph the line x is less than 4, we need to remember that if it's x equals, that's going to be a vertical line. It's a strictly less than, so we're going to have a dashed line. And if we were to pick a test point to graph this, well, what values are less than 4? It's going to be all these values to the left of the line. And now we need to graph the horizontal line, remembering that y equals is a horizontal line. We need to graph y is greater than or equal to 2. This is going to be a horizontal solid line because it's greater than or equal to. And then what values are greater than 2? Those are going to be all the values above the line. And so then if you look, and I have colored pencils if you would like to borrow them when we're doing our work in class, where do the shaded regions overlap? We need to shade darker there, and it's going to be this area up in here. So we're going to shade darker there so it's perfectly clear where the shaded region is, and we're done. The next example, we have 4 lines we need to graph. Well, the first 2 lines are vertical lines because they're x equals, so we can go ahead and graph x is less than or equal to 3. That's going to be a solid vertical line on 3, and we're going to shade to the left. Keep in mind, it looks like my shading is only going to the x-axis, but it actually is everything over here. We also need to graph and shade x is greater than or equal to -2. So again, that's going to be a solid line. And values greater than are going to be everything to the right. So right now, our region is going to have to be bound somewhere between these 2 vertical lines. Now we need to go ahead and graph x plus 2y is less than 8. So go ahead and pause the video and solve that for y. So when we solve that, we get y is less than -1/2 x plus 4. So again, we're going to graph that by going up to 4 for our y-intercept, and then down 1 to the right 2. And we're going to graph that until we meet the edge of the graph. That's going to be a dashed line because it's strictly less than. And then if we pick a test point, if I pick 0, 0 and plug 0, 0 up into my original equation or my y equals mx plus b equation, 0 plus 0 is less than 8. That's true, so I'm going to shade below that line. And now go ahead and solve the last equation for y. Subtracting the x over, and now we need to divide by -2. Make sure you flip the inequality when you divide by that negative. And so now we get y is greater than or equal to 1/2 x minus 1. So our y-intercept of 1, and now we're going to go up 1 over 2, again until we get to the edge of the graph. That's going to be a solid line as well. And again, if we pick a test point, 0 minus 0 is less than 2 if I pick the origin. That's true, so it's going to be shaded above. And this is why I tell you need to shade very neatly, and possibly with colors is going to be a lot easier. So where does this shaded region overlap? This shaded region overlaps in, it's not quite a triangle because it stops at that vertical line, but it's going to be this trapezoid, if you remember what a trapezoid is, two parallel lines. And that's our solution. And now for our final solution. Again, we have to solve both of these equations for y, so go ahead and pause the video and go ahead and solve both of these equations for y. When you solve the first equation, again, you're dividing by a negative, so don't forget to flip the inequality. You should get y is less than or equal to -2x minus 4. And when we do the second equation, it's a matter of simply subtracting that 2x, so we get y is greater than -2x minus 3. And so we can see by the fact that these have the same slope but different y-intercepts that they are parallel lines. We can't necessarily assume that they are no solution. Before we actually graph this and determine that, this is why. If I have two parallel lines, if I shade both of them to the outside, it would indeed be no solution. However, if I have to shade both of them on the inside, let's say I shaded this line this direction and this line this direction, then that solution set would be just what's in between. Or again, I could be shading both of them to the right, so the solution would be just to one side of one of the lines. So again, don't make the assumption that just because they're parallel, they are a no solution. So let's go ahead and graph both those lines. Pause the video and go ahead and do that. So when I graph this first line, and now I pick a test point of 0, 0, and if I plug that into the original equation, 0 minus 0 is greater than 8. And that is false, so I'm going to shade to the left. Now let's go ahead and graph the other line. This line is actually graphed kind of wonky, actually when I drew the line. But these are going to be two parallel lines right next to each other. I didn't draw a very nice straight line for my red line. But again, if I pick a test point of 0, 0, plug it into my original equation, 0 plus 0 is greater than -3. This one is true. So in this case, I am in fact shading on the outsides of those lines, so there would be no solution for this system of inequalities. This is the start of a new chapter, a new beginning to start asking questions. And some of this material might be starting to get new for some of you, and some of it might not. So please don't be shy. Come to class and ask questions. And of course, don't forget to go back and do the notes check. And we'll see you on tomorrow in class.